We have a particle, mass 2 kilograms, and two forces are being applied to it, a constant force and a variable force. We're asked in part A to determine the value of T when the forces are in equilibrium. So let's work out the resultant force. F is going to equal this, and I'm going to write it in column form, I just find it a little bit easier. Minus 8 minus 54 plus 4t 6 times 2t minus 1 all squared. All right, add them together. And this is going to equal 0 when P is in equilibrium. So it must be that 4t is equal to 8 and t is equal to 2. And I can just check by substituting it into the bottom part as well. I'm going to get 6 times 3 squared minus 54. I'm also going to get 0 here. Note for that one, I think I would have got a negative time solution because I've got a quadratic, but they have to both be 0. And so I don't need to look into that. I can just use the fact that t is 2. Right, it's given that P is at rest when T is 0. Okay, it's going to underline that. That will come in useful later on. Determine the speed at the instant when P is moving due north. Okay, so to get the speed, we're going to need the velocity. So F equals ma, which means A is going to, in this case, is going to be 1 over m times F, or half F, which is going to become 2t minus 4, 3, 2t minus 1 squared minus 27. That's my A. Now that is actually dv by dt. So to get B, we can integrate. And the mark scheme, and quite often in questions like this, I see people splitting it into the ij form, component form, and integrating it, but I don't think there's anything wrong with just sticking your column vector inside an integral. So I'm going to get t squared minus 4t. And then I have got to use a chain rule here. So I'm going to add 1 to the power, divide by the new power. It's going to give me 2t minus 1 cubed. But then when I differentiate this, I would also times by 2. So I need to divide by 2. And then minus 27t here. But there's a constant. There's going to be a constant for the x component and the y component. So I'm just going to label it a little vector c. Okay, when t equals 0, v is equal to 0. We were told that it was at rest. Therefore, 0 or 0, 0 is going to equal the top. When I put 0 in, I just get 0. The bottom, however, I'm going to get 0 minus 1, which is just minus 1, cubed to give minus 1 again, times by a half. I'm going to get minus a half. And then the minus 27t just gives 0. Plus c. That means that c is going to be 0 a half. And therefore v is going to be t squared minus 4t half times 2t minus 1 cubed minus 27t plus a half. That was quite a lot of work. We're not actually done yet. So determine the speed when the particle is moving due north. So particle moving north when the x component of the velocity is 0 and the y component is not 0. If it was 0 as well, it would just be stationary. So let's deal with the first bit. We can factorize out the t. T times t minus 4 is equal to 0. So t is equal to 0 or 4. But I can reject this one because I already know it's at rest. If I forgot that, I could substitute it back in to the y component and I would see that it does equal 0. So then here the is then going to equal 0 times, I can just substitute 4 into here. And I get 64. So speed here, it's actually, I don't need to do anything else, don't need to do Pythagoras because remember, it's moving north, it's just going to equal 64 meters per second. Right, one more part to go. We're asked to determine the distance between the positions of P when t is equal to 0 and t is equal to 3. So first up, I need the displacement. And that is going to be given by integrating. By the way, you could use s, but typically r is used for the position. So I'll use that here. R is going to be the integral of v with respect to t. So the integral of t squared minus 4t, and then all the rest of this, I'm just pulling down from up here. And then got the chain rule again. So increase the power by 1, divide by the new power. Gives 1 over 8, and then divide by 2, so I'm going to get 1 over 16. You can always check back, like if I differentiate, I would times by 4, I would times by 2, that would take me back to a half, I'd lower the power. Yeah, that's correct. And over here, I'm going to get minus 27 over 2 t squared plus a half t. Don't forget there is another constant. Okay, let's look at what happens when time is 0. R is going to equal 0. And then over here, I'm going to get 1 to the power of 4, which is just 1 times 1 over 16. So I'm going to get 1 over 16 plus this k. T is equal to 3. A little bit more calculation to do. So 3 cubed divided by 3 minus 2 times 3 squared, which gives minus 9 for the x component, the position. Okay, and here I get minus 1295 over 16. Plus k. And the change in r is therefore going to be the second one minus the first one. I'm going to get minus 9. And then I need to do this answer minus 1 over 16, which gives minus 81. Hey, that's nice. And the k's cancel. So the distance, I can just use Pythagoras. Because let me just, so I'm going like this way and this way with my displacement. So I start here, I end up here. So the distance is then this hypotenuse. When you're squaring a negative, you can just ignore the sign. And at this point, I don't think I need to show any more work in. 81.498. Or 81.5 meters. All right, quite a lot to do there. And this variable acceleration crossed with vectors, variable acceleration in 2 dimensions. We've got vectors going on question. Well done.